So, somewhere between the apple that fell on Newton's head and the multiverse that might actually hold thousands of versions of you lies the incredible landscape of science theories. Not facts, not rules, but our best guesses. These models that try to describe this thing we call reality. They're like superpowered magnifying glasses that help us peer into this universe of ours, from the tiniest particles to the grandest galaxies. And today on the archive, we're going to dive deep into the 5 science theories that have shaped and continue to reshape how we think about everything from gravity to quantum, string to space, and the mysteries that are still left unsolved. It's going to be a wild ride, so buckle up.
At the intersection of science and technology, imagination and creativity converge. This is where their stories are told. Welcome to the archive. The science and tech of today and tomorrow.
Now, let's start with the classic, a theory that completely flipped our understanding of something we all experience every single day. And I'm talking about gravity. But gravity, you're going to notice when I'm actually talking about the theories that we're going into, is actually the culprit. One of the things that actually seems to be a mystery in a lot of the theories that we present today. It seems to be the one caveat that nobody can seem to grasp or handle. So with that, let's talk first about general relativity. So before 1915, most of us, if we thought about it at all, and I think about it way too much, but for those of us that thought about it at all, we pictured gravity like Isaac Newton did. It's a mysterious force pulling things together. You drop an apple, it falls. The Earth pulls the moon, it stays in orbit. Simple, right? Then came along a brilliant guy, you might know this dude, Albert Einstein. Now, Einstein didn't just tweak Newton's law, he pretty much demolished the very idea of gravity as a force in a way that we've really never understood before. Instead, his 1915 masterpiece told us something mind-bending. The universe isn't just empty space with stuff floating around in it. It's like a giant flexible piece of fabric. Space and time aren't separate things, they're actually intertwined. Part of the same structure, if you will. You've probably seen this type of visual before, but just going to put this into perspective. Imagine you stretch out a big trampoline. Now, you place a big bowling ball in the middle. What happens is the trampoline sags right in that middle area, right? Now, if you roll a small marble nearby, it doesn't get pulled by the bowling ball. Instead, it rolls towards the bowling ball because the trampoline itself is warped. And that's essentially how Einstein described gravity. Planets orbit stars not because they're being yanked by it, but because they're following the curvature of space-time. And it's created by the star's immense mass. And here's where it gets even wilder, is that general relativity also tells us that gravity literally warps time. I mean, time itself can tick slower or faster depending on how close you are to the massive object. It's a tiny effect in our everyday lives, but it's real. So why does this theory matter so much in the grand scheme of things? Well, for one, and I know I use this a lot, but GPS wouldn't work without general relativity. The satellites that make GPS possible, Global Positioning System satellites, are orbiting Earth, where gravity is slightly weaker than here on the ground. This means their clocks tick a tiny bit faster than the clocks on Earth. If GPS systems didn't account for this time warp in some way, your navigation would be off by miles each day. It's also how we understand truly cosmic phenomena like black holes. Those, mysterious regions where gravity is so strong that not even light itself can escape from it. It helps us understand neutron stars, incredibly dense remnants of collapsed stars, and the bending of light from distant galaxies, what we call gravitational lensing, where a massive galaxy acts like a cosmic magnifying glass, bending the light from even more distant objects behind it. So why is it still a theory? Because it still has its limits. It breaks down under truly extreme conditions, like the infinitely dense center of a black hole, or the very first moments after the Big Bang when the entire universe was incredibly compact and hot. And at these points, the equations of general relativity give us infinities. And in science, infinity usually means, SpaghettiOs. Maybe an old reference. But it's just basically saying that something isn't quite right here. Our current understanding isn't complete when it comes to that theory. And there's an even bigger problem. I mentioned this already, but general relativity has issues with gravity, just like you'll hear about a lot of other theories and why gravity is kind of a pain when it comes to figuring this stuff out. So, general relativity doesn't play nice with other scientific success stories, quantum mechanics. The two speak very different mathematical languages. One describes the vast cosmos and gravity, and the other is the incredibly tiny subatomic world. And they stubbornly refuse to fit together in a perfect puzzle. This kind of unified picture. Unified. Let's try that one. It's like having two halves of a beautiful puzzle, but they just won't snap together. And we all know how irritating that is when you think you found the perfect piece, but it doesn't fit, right? Maybe. So while general relativity has passed every single test we've thrown at it, from observations of light bending during a solar eclipse by Arthur Eddington in 1919, which famously confirmed Einstein's prediction, to the recent LIGO experiments, and these are detecting gravitational waves or ripples in space-time itself. Ripples in space-time. Einstein predicted that. Pretty cool, right? We still don't know how it fits into the full, complete picture of our reality. Which brings us to the next contender, the one that describes the universe getting really, really, really weird. If general relativity is the grand symphony of the cosmos, then quantum mechanics is the chaotic, unpredictable, and utterly mind-bending jazz solo of the subatomic world. It's the revel of the science family. This theory describes how matter and energy behave at the smallest scales. So the realm of atoms and the particles that make them up. And what it tells us is, it's just really bizarre and weird, the subatomic level. I'll learn how to talk someday. It says that particles can be in two places at once, or even spin in opposite directions until you actually look at them. The observer effect? Heard of it? It's like trying to describe a blurry photograph where the more you focus on the one detail, the fuzzier another becomes. Reality in the quantum realm or the quantum world is not a fixed solid. It's a fuzzy, probabilistic, and in some interpretations, observed into existence, if that makes any sense to you at all. So the key players in the development of quantum mechanics in the early 20th century were a whole cast of brilliant scientists. You might have heard some of these, like Max Planck, who first proposed that energy comes in discrete packets, or I think he called them quanta. Then there's Niels Bohr, who developed a quantum model of the atomic. And of course, you've heard of Werner Heisenberg. He did the whole famous uncertainty principle. And then the godfather of them all, the one you've heard about so much, Erwin Schrödinger, who didn't like his cat. I don't know. These pioneers and many others slowly pieced together this strange new understanding of reality. So why do we believe something that sounds so utterly unbelievable? Because it works. And oh, does it work. So think of lasers. The tiny chips in your smartphone, semiconductors, MRI machines that see inside your body, even nuclear power. All of these technologies and many, many more are built on principles of quantum mechanics. It's an incredibly successful theory when it comes to predicting and explaining the behavior of the tiny world. But wait, there's a catch, and it's kind of a big one, even though it's about the tiny world. Quantum mechanics doesn't play nice with guess who? Gravity. Remember how general relativity and quantum mechanics are like two halves of a puzzle that just don't fit? And this is where that conflict really comes to head. The math breaks down when we try to combine quantum mechanics, which works well for like microscopic, with general relativity, which works well for the macroscopic and for gravity. So this fundamental incompatibility is the biggest challenge in modern physics today. And this brings us to our most ambitious and perhaps most controversial idea yet, a theory designed to bridge the very gap between the two. Can you guess what it is? It's all right, I'll tell you, because that's what I'm here for. String theory. Now, imagine a guitar string. When you pluck it, it vibrates, and depending on how it vibrates, it produces different musical notes, right? Now, what if everything in the universe, from the smallest fundamental particles like electrons and quarks to the vast galaxies themselves, wasn't made of tiny little dots or particles at all, but of an unimaginably tiny vibrating string, or strings in that case? This is the core idea behind string theory. And it's not just one theory, but rather a family of related theoretical frameworks that emerged in the late 1960s and gained significant traction in the 1980s. And some of the key figures in this, you're thinking of John Schwartz, Michael Green, Edward Witten, and among many others who explored the mathematical depths of string theory. Remember the word mathematical. It'll matter, mathematically speaking. String theory says that what we perceive as different fundamental particles like electrons, photons, or quarks are actually just different vibration modes of these incredibly tiny dimensional strings. Just like how one guitar string can make many different notes depending on how it vibrates, these strings can actually produce all of the different particles we observe simply by vibrating in different patterns. And here's where things get even wilder when it comes to vibrating. String theory often requires the existence of extra dimensions. A lot more than the 4 we usually experience, 3 of space and 1 of time. We're talking 10, 11, or maybe even more dimensions. Now, before you start wondering where these extra dimensions are, the theory suggests that they are curled up so tightly, so infinitesimally small that we can't perceive them directly. They're like a garden hose seen from far away. Looks like one dimension, but up close you see it as a 2-dimensional surface wrapped around it, if that makes sense at all. So why do smart people dedicate their lives developing a theory that sounds so fantastical? I think that's a fair question. I think most people want to know that. Because it offers a truly compelling prospect. It could unify all the forces of nature. Kind of like the Avengers of the forces of nature. I had to slide that in there. Remember that big problem we talked about with general relativity and quantum mechanics not playing so nice together? Well, string theory aims to solve that. It suggests that gravity, electromagnetism, and the strong and weak nuclear forces, the forces that govern interactions within atoms, are all just different manifestations of these vibrating strings. And if true, it would be the ultimate theory of everything. Not just the movie that starred Eddie Redmayne, which I thought was really cool. Check it out if you haven't. The theory of everything, a single elegant equation that describes the entire universe. That sounds pretty awesome. But there's a problem, and unfortunately it's a pretty big one that leads to a lot of debate. There is absolutely zero fundamental proof that string theory actually is a thing. Let me say that again. There is absolutely no experimental proof for string theory. None. Zippo. Zilch. So these strings are so incredibly tiny, far, far smaller than anything we can currently detect with our most powerful particle accelerators, like the Large Hadron Collider. Critics argue that a theory that cannot be tested, that cannot be verified or disproven by experiments, and even though it might be mathematically beautiful and incredibly elegant, but is it really truly science if you can't test it? And if you can't test it, how do we know it's describing reality? So this lack of experimental verification is the biggest issue and the reason it remains really still a theory in the speculative sense. And rather than a widely accepted explanation like general relativity or quantum mechanics, it's bold, it's beautiful, I guess, if you're into math, but it's a guess nonetheless for string theory. All right, we're going to go right into the grandfather of theories and models, okay? And this is described as the incomplete masterpiece. And typically what you hear about in the news when they say it defines the current standard model of physics. At least that's what I hear on my news feeds. We are talking about the standard model. Now we're going to pivot from the speculative to the incredibly successful. This is going to be like the Olympian of physics and models and all that stuff. Let's talk about the theory that does work and works really, really well. And it's called the standard model of particle physics. Welcome. So if string theory is the elegant guess, then the standard model is the incomplete masterpiece. It's our current best description of the fundamental particles that make up everything around us and the forces, excluding gravity, that little nutcase, by which they interact. So this model was built piece by piece throughout the 20th century by countless physicists. It's probably one of the most truly collaborative efforts, bringing together concepts from quantum field theory, electromagnetism, and the theories of the strong and weak nuclear forces. Think of it as like a comprehensive rule book for the subatomic world. So the standard model describes a zoo of subatomic particles, like quarks, the word I can't always seem to say right. These are the building blocks of protons and neutrons, which make up the nucleus of every atom. Then you've got leptons. This group includes the electron, which orbits the nucleus, and neutrinos. These are tiny ghostly particles that interact very rarely. And then you got bosons. These are the force-carrying particles. I mean, for example, photons and the bosons that carry electromagnetic force, you're thinking of light and electricity. And then the gluons, carrying the strong nuclear force, which holds quarks together. Gluons. That makes sense. And W and Z bosons carry the weak nuclear force responsible for certain types of radioactive decay. Did you get all that? Good. And finally, there's one more. A famous one that kind of became news a few years ago. Have you heard of it? The Higgs boson. The famous Higgs boson. This particle, predicted by the Standard Model for decades, was finally discovered in 2012. Before the world came to an end. If you kids don't know, ask somebody. And guess where it was discovered at? The LHC, the Large Hadron Collider. Its existence really explains why other fundamental particles have mass. It's like a universal molasses field that particles move through. The more you interact with it, the more sticky they are, and thus the more mass they acquire. And the reason the Standard Model is so celebrated is its incredible accuracy. It has predicted the existence of particles and their interactions with stunning precision, culminating in this triumphant discovery of the Higgs boson. But, and this is significant as far as buts go, it's not complete. For all of its triumphs, the Standard Model has some glaring omissions. It doesn't include the one culprit that causes a lot of issues in other theories, gravity. I mean, that's right. The Standard Model describes everything except the force that holds us to the Earth and governs the motion of galaxies. This goes back to our earlier point about general relativity and quantum mechanics not meshing. Gravity is always the problem. It also doesn't explain dark matter. We have an overwhelming amount of evidence from astronomical observations that there's this mysterious invisible substance out there called dark matter. It doesn't interact with light, but its gravitational pull is crucial for holding galaxies together. And the Standard Model of physics has no particle or mechanism to account for it. It doesn't explain dark matter or, for that matter, dark energy. And this is an even more mysterious force that seems to be accelerating the expansion of our universe. So again, the Standard Model is silent on all this. So while the Standard Model is an incredible achievement, it's like we have a perfect, incredibly detailed picture, but it's a picture of only about 5% of the universe. That's a lot of the universe we don't understand. 95%, maybe. We have a perfect picture of the wrong puzzle, really. The vast majority of the universe, the dark matter and dark energy, remains outside its scope. This means that while it's undeniably successful, it's also undeniably incomplete. Way to go, Standard Model. All right, so we've talked about those, but let's go just a little bit beyond. And I'm talking about loop quantum gravity. And also the emergence of WTF type sciences. So we've talked about general relativity, you know, the big stuff and gravity and all that jazz. And we talked about quantum mechanics, the small, weird stuff. We've talked about string theory, the guitar of the universe. And then we talked about the Standard Model, the incomplete success. Sometimes my parents call me that. Still dealing with stuff. What about the next? What are the new ideas that are trying to solve some of these big problems? That's a great question. I'm glad you asked. There are a few new players when it comes to the ambitious attempts to move beyond our current understanding and tackle those fundamental incompatibilities. One major contender is loop quantum gravity. I call it LQG. And while string theory tries to reconcile gravity and quantum mechanics by adding extra dimensions and tiny strings, LQG takes a different approach. So it was developed by physicists like Carlo Rovelli and Lee Smolin. LQG suggests that space itself, the very fabric of space-time, isn't smooth and continuous like a sheet, and instead it's made of tiny discrete chunks. It's like pixels on a screen, or like perhaps a very fine interwoven network of loops, and it tries to quantize gravity? Is that a thing, quantizing? Well, it is today. So just like energy and matter are quantized, New word, just made it, I think. Quantum mechanics, the idea is that if space and time themselves are made of tiny fundamental units, then general relativity and quantum mechanics might finally shake hands. And the challenge here, like with string theory, is the lack of experimental ways to test these incredibly small loops of space-time. Another fascinating and even more radical idea is the emergent gravity. This view suggests that gravity isn't a fundamental force at all, but rather an emergent phenomenon. Much like temperature emerges from the collective motion of countless individual atoms, some proponents like Eric Verlinde suggest that gravity might be an illusion caused by entropy, a measure of disorder or information. Entropy, when things break down. Easy enough. Rather than this fundamental force, this is a very new and highly debated concept, but it represents a truly outside-the-box way of thinking about gravity. One that might actually finally reconcile with the quantum world if true, and it would completely redefine understanding of one of the most basic forces in the universe. But it don't stop there, we got others. In some theories, we go even further, asking fundamental questions that border on philosophy. What if time itself may not be fundamental? Some physicists suggest that time is an emergent property or even an illusion rather than a fundamental dimension of reality. Others ask, what if consciousness plays a role in how reality is formed? This is a highly controversial area often referred to as WTF science. I can't say what that is, I'm sorry, because it's got bad words, so you know what it is, you can look it up, there you go. While these ideas are far from mainstream, they illustrate the boundless curiosity and relentless questioning at the heart of scientific inquiry. We are officially past the edge of established science here when it comes to these type of ideas, and it's really peeking into the realms of where math meets philosophy, and even sometimes, just sometimes, where even the most brilliant minds can feel a touch of madness. I gotta work on my evil laugh. Alright. So, after the whirlwind of the tour of the universe's biggest mysteries and my best attempt to understand them, what is a scientific theory really? I probably should have started with that. It is what it is. So, a scientific theory is not just a guess, like saying, I guess it's gonna rain tomorrow? It's really far from it. At least I definitely hope it is. A scientific theory is a powerful explanation for a wide range of observations and experimental results. It's built on evidence, rigorously tested, and has predictive power. It's a tool, a way to map that we know, and perhaps even more importantly, to poke holes in what we don't know. So theories are frameworks that allow us to organize our knowledge, make sense of the universe, and guide us towards new discoveries. But here's the profound truth. Every single theory we discussed today, from general relativity, quantum mechanics, string theory, the standard model, and even the emerging ideas, these could be incomplete, they could be flawed, or even wrong in some fundamental way. And guess what? That's okay. In fact, that's what makes science beautiful, in my opinion, because science isn't about finding absolute certainty and declaring, we're done. It's about continuous process of curiosity, questioning, testing, and refining our understanding of the universe. It's about building better and better maps, and even if we know the territory is infinitely complex, we still do it. So I'll leave you with this one thought, this one kind of profound thought that I had in my head. If the universe is a grand unfolding story, then these theories are often the very best drafts that we have of it. They are a valiant attempt to make sense of the cosmos, to write down its secrets in a language that we ourselves can understand. And maybe, just maybe, the final chapter hasn't even been written yet. And I'm pretty sure it hasn't. We're just not the ones writing it. The journey of discovery is never ending. So until next time, stay curious, stay human, and tune into the archive. And as mentioned at the beginning of the podcast, if you haven't already done so, and you like my content, please, click like, subscribe, leave a comment. Love to hear from you. Till next time.